Hello, everyone. It's great to be here. My name is Sid, and I'm very excited to present the work we have been working on at Systopia Lab on the Osmosis project. This work has been done by many students, undergraduate and graduate, and with constant input from all the faculty. And first, I would like to talk about what the larger research question we are trying to answer, and then we'll go into how we use CellulOS to answer those questions. The goal is to compare isolation mechanisms. So let's briefly talk about the history of isolation mechanisms. In the early days of computers, we were just happy that we could run something. We didn't care about isolation. In the 60s, we got virtual memory. Soon after that, we got processors with multics. In the 1970s, we got virtual machines, but the goal there was to do time sharing. With multiprocessors, we got threads. In the late 90s, we again got virtual machines, but the goal this time was isolation. With Mogul and Banga, we got resource containers. And the contemporary form of containers, which most of us think of as Dockers, came in early 2010s. We also had a lot of academic work. I've mentioned one here called lightweight context, which provides address space isolation, intra-address space isolation. And while all this is going on, there is like resurgence of virtual machines in the form of various lightweight VMs. Kata containers is one, Cap VM is cherry-based virtual machines. We have Verteens, Unicraft, a whole lot of them. What is the problem with this landscape? I tend to think of all of these as different design points in a big design space. And there is no way to compare them. Like if you think of Podman and Docker as two container frameworks, there is no precise way to say what isolation I'm getting or not getting if I deploy my application in these two. It's hard to compare them in any kind of principled way. We might be getting too little or too much isolation. And as the unintended consequence of that is you might be sharing hardware and software resources which you don't know about. It's also very easy to misconfigure. So we want to build a model to enable precise comparison of isolation mechanisms. This model should be able to describe the entire system, all the tasks and the resources in the system, and how these resources depend on each other. And then we want to use this model to answer these kind of questions. How difficult it is for one task to affect another task. Or if a task misbehaves, what can be the impact of that misbehaving task? And how do these answers change based on how you go from one isolation mechanism to another, or if you change the OS architecture itself? So this brings to the agenda for today. I just went over the goal, which is to enable developers to be able to compare isolation mechanisms. We built a model called Osmosis to allow formal reasoning to do this. And we built a SEL4-based operating system called CellulOS, which exposes the protection domain state to get the osmosis state out of the system to enable the comparison. So let me briefly go over what the model itself looks like. So in our model, we have a concept of protection domains. So in this picture, we have the process and the kernel as two protection domains. The kernel as a hold edge to a resource space called VAS, which is for virtual address space. A resource space is a pool of resources. Another resource space the kernel has access to is all the DRAM in the system. And a process using the dotted edge, called a request edge, can request resources from another protection domain. So in this case, the kernel. And what it'll get by requesting, it'll get a resource. So in this case, it'll get a code page resource. The resource is held by the process because it owns that code page, and it is a subset from the resource space. So resources are carved out of resource spaces. Resources also map to other resources. So virtual memory page maps to some DRAM page. That DRAM page is a resource, which again maps to a resource space. So it is a subset of a resource space. Now, with this, let's look at what a mmap system call would look like. So in that scenario, the process would request the kernel to give it a new region of virtual page. And in return, let's say it got a heap page. And then when it faulted on it, a new page will get allocated, which will again be a subset of the resource space. So this model graph changes as the system goes on. In short, what this is supposed to say is we are trying to show the entire system as a graph. The graph has 3 types of nodes for protection domain, resource, and resource space, and 4 types of edges. So this is what a real graph would look like. So this is a visualization in Neo4j. It has 4 protection domains running, an application talking to a file system, which is backed by a block server, and there's a root task which orchestrated all of this. So the blue nodes are files which are shared between the application and the file server. The files are backed by blocks. The blocks are shared between the file server and the block server. And the block server has access to a whole bunch of virtual memory, which is backed by physical memory. And so this is the kind of thing, pay attention to the orange node in the center. It's a physical memory page which is shared between the file server and the block server, but also has access to the root task. Now, if you know how you've implemented the system, this is not surprising. This is the shared page between the file server and the block server for communication. But the root task still has a capability to it. So for somebody who has built the system, this will be obvious. But for somebody who has not built the system, they could use Osmosis to find out, like, oh, this is shared. I did not realize something like this would happen. So what kind of precise questions we want to answer? We want to be able to calculate precisely what is the trusted computing base for a given production domain. So what are the set of domains it depends on to function correctly? Similarly, we want to understand what is the impact boundary of a production domain. If a given production domain misbehaves and does something bad, what are the other production domains in the system it can impact? To do this, we express trusted computing base as a union of 5 graph queries. Each one of them captures a certain type of interaction. So shared resources query says that, tell me all the protection domains in the system which share resources of a certain type with certain access permissions with my given protection domain X. So this can help us find out which other protection domains can affect its confidentiality, integrity, and availability, depending on the permission. Shared resource spaces are more about availability. So think about if 2 processes share the same C group, they can affect each other's availability. Resource space servers are protection domains which provide resources to a given protection domain. So file server would be an example of a resource space server. So that obviously is in the TCB of my protection domain. Similarly, any other protection domains which share resource space servers are also in the TCB. And can control is finally any protection domain that has direct access to control the given protection domain. Like for example, if you can send a kill signal in Linux, or if you have the thread control block capability in SCL4. So what we're trying to do is we are trying to precisely define TCB in terms of Osmosis model queries, and the whole query is parameterized. You can focus on the things you care about, and you can tweak the types of resources you care about. We have a similar definition for impact boundary also, but we will not go into that today. So let's look at the first query in a little bit of detail. So shared resources query eventually boils down to a breadth first search query. So imagine for PD1, we want to find out all the resources that has access to. So we run that BFS query, which traverses only hold and map edges in a particular direction and looks at only particular types of resources types. And then it tells us that, hey, PD1 has access to only R1 resource. Similarly, PD2 has only access to R2 resource. So their intersection is null. So, oops. What we'll say here that PD1 and PD2 do not share resources of that particular type. But if I were to run another query, say shared resource spaces, then it will show up that RS1 is a shared resource space for those two production domains. So the kind of things we want to answer with that is, here on the left side, we have a key value store application running on SCL4 with the root task in the middle. So on the left, I'm showing a static setup where the root task, once it sets up the key value store, it can no longer impact it. And on the right is a more dynamic setup where the root task can kill the key value store. So something like this, the difference between those two scenarios will show up as the difference in the result of the query. So the can control query will show that for KVS, the key value store, in the static system, only SCL4 kernel can impact it. But on the dynamic system, both the root task and the SCL4 kernel can impact it. Other kind of things we can talk about is, this is a deployment of the key value store in an application on CellulOS on the top left, and this is one on Linux. So on the top left, we see that the key value store in an application cannot send signals to each other, they cannot kill each other. But on Linux, if you're running it as the same user, they can impact each other. So the can control query result will be different. Similarly, if I'm talking about virtual machine deployment, so I have a VMM, an application, root task, and a PDVM is the entire virtual machine. Again, the same thing. The application cannot kill the PDVM, but on Linux, if you're running as the same user, the VM is just QEMU, it can kill, and vice versa. So again, this thing will show up as difference in the queries. And if you talk about the guest process inside the VM, the GKVS, then the answer remains the same because both of them are effectively the same. So that's about the model and the kind of questions we want to answer. I obviously took example of just one of them, the can control query. We didn't go into all the other queries. But let's get into the SCL4 part of it, the CellulOS operating system. Our objective was to build an OS which enables us to easily track the entire model state and extract it easily. We picked a capability-based microkernel because it tracks all the resources explicitly. It gives us fine-grained access control. And when I started the project in 2021, SCL4 was the best documented microkernel out there, and it's only gotten better since. So this is the architecture of our system. We have a root task. We are not using microkit because when I started, microkit was not there. So I just took off SCL4 test and started hacking at it and built it from there. Along the way, we have ported a file system, which is XV6FS. We created a RAM disk, which is just memory backed. And the block server is again a port of the HDDF driver into our system. The key value store at the top left is a port of SQLite. The application is just a simple application which talks to the key value store over IPC. And the VMM is again a port of the microkit VMM brought into our project. And the VM is just a guest Linux. So a typical deployment would work like this. You would set up your system, get into a steady state. In the background, CellulOS is doing the runtime tracking. And you extract the state at some point, and then you can, using that state, you can import it into a graph database, or you can use a network-x package. There's a typo there, a network-x Python package, and then you can run the kind of queries I've shown earlier on to answer the questions about TCP and impact boundary. This is the main example we have in our system. So we have an application which talks to SQLite, which talks to a file system, and which talks to either a RAM disk or a HDDF driver. And we had to do some work with porting libc to make sure it works in our system. Resource tracking, every resource is explicitly tracked, and we use badge endpoints to track every resource. And we split the 64 badge into a type of resource, a resource ID, server ID, and owner ID. The root task tracks every resource, but it does not know every relationship. So it does not know all the edges between every resources. So that's why it needs to talk to some of the resource servers to get that information, which leads to an interesting deadlock. So I'll talk about that next. So imagine an application has talked to a file system to open a file, and at the same time, another application has asked root task to extract the entire system's model state. So as part of giving a file back to the application, the file server also has to tell the root task that, hey, I'm giving this file to this application, because the root task knows about all the resources in the system. And the root task needs to talk to the file server to get the partial model state. What is the model state maintained inside the file server? So this leads to a deadlock. The way we got around that is we created a concept of a work queue. So the root task never actually makes a blocking call to the file server. It just sends a signal and says, hey, I have some work for you. Please get back to me when you are ready. We use the bounded notification concept from SEL4. And we also extract the model state from inside the Linux guest, and to create an Osmosis model graph for the entire system, the guest and the host combined. So to do that, we did something very hacky. We did not hack the Linux kernel. We said, let's look at the /proc and /sys file systems and see what information we can get out of it. Here is a table of what we use to get what information. We don't need to get into that right now. But it was quite challenging because there was no central place in Linux where we could look to get all the resources in the system. So we did the best we could with the information available in proc. And this is a little bit about our journey into doing this project. We're a small group of graduate students, just me initially, then few undergraduate students have come and gone through the years. And learning how to do this on a capability-based paradigm was difficult for me personally to get started. But the community has been extremely supportive, be it the mailing list or be it like one-on-one support from Nick and Ivan with MicroKit. And as MicroKit developed, we found a lot of help with that. We just took the drivers, pulled it into our system. We knew that Odroid is going to be there, so I just bought the Odroid board and I said, let me just develop my project on that. And a couple of coursework has also been very useful. The Barrelfish course by Professor Achermann at UBC, and the UNSW SEL4 course by Professor Heiser. And so in summary, we implemented the root task completely from scratch. We developed the full workflow to track and extract the Osmosis model state, and it currently runs on QEMU and Odroid. Also did a bunch of Linux work, ported SQLite, file system, virtual machine monitors, some drivers, wrote a bunch of code. And we're trying to figure out, like, this model that we've built to compare isolation mechanisms, can we use it to do other things? Can I say something about isolation properties as it changes through time? Right now, I'm just looking at a snapshot of the system, and there's another graduate student who's looking at using this model to do some kind of formal proof about, hey, if it's set up this way and only these transitions are allowed, what can I tell about isolation in the system? And the second part, which I'm doing, is if I can express an isolation mechanism as a graph, can I explore the entire design space of isolation mechanisms? How do I mutate my graph in a constrained way to find every isolation mechanism out there? And that one is very much up in the air. I have no idea. And this is something this is a meme which has been around for a long time. Like programming in assembly is like working with a knife, and programming in Python is like an extremely complicated gun. And I draw parallels with working on a microkernel and programming for Linux. I find this useful. If somebody finds a gun offensive, I'm sorry about that, but it just felt appropriate. And that's all. I'm happy to take questions.
So you mentioned reasoning about the evolution of authority in the system and isolation properties. So if you can extract the capability distribution in SL4, then I think the thing that would immediately occur to me is to look at the assumptions of, say, like the integrity proof, right? That says, I mean, the integrity theorem says that if certain properties hold about the distribution of capability of systems, then you have guaranteed integrity. So one way to approach that might be to, you know, monitor that property, right?
Perhaps I have not looked at the proof
Okay.
at all. So we didn't come at it from the formal verification was never the objective. The objective was to compare.
Yeah.
So now I'm like, okay, now I think we might have verified.
Right. Okay. So that's like a where you'd like to, yeah, an idea you have now for the future, rather. Yeah. Yeah. But that might be a.
Another thought related to your first bullet point of future work might be to, instead of just visualizing and querying sort of the outcome of these of what you're observing, allow users to define policy on this model graph and either detect or you know, abort processes when those policies are violated. It seems like a nice direction.
So isolation is not the same as trust, right? When I have a I/O service that processes data from a client, it is not isolated from the client, but if it's done properly, it doesn't trust the client, right? So does your system help in distinguishing this kind of relationships?
What my system can tell you is you are relying on this thing. Is it not on? Is it on? So yeah, my system will not tell you whether you can trust it or not. What it will tell you is that, hey, this is something you are relying on, and there might be other reasons why you are trusting it. Like it is formally verified, or like it was provided by a trusted authority. It'll just help you identify the things you're relying on. Does that answer? Any other questions?
You talked about how part of your work included building tools for kind of inspecting the state of a Linux system to compose that information with the information from your SEO4 native part. Have you considered applying or how you could apply that tool to kind of audit solutions that are already out there, like, you know, container stuff that people use in Linux?
Yes, so that is some work we have done. We have a paper, it was in submission, it got rejected, basically, to use that tool to compare 4 or 5 different container technologies and how they set up their namespaces differently and how they set up their seccomp differently. All that kind of shows up in the Osmosis graph without you needing to know about how it was exactly set up.
Okay, thank you.
All right, thank you everyone.